Hi there, my name is Christian Fain, and today I'm going through my thesis, which is on a real-time diminished reality approach to privacy in mixed reality collaboration. So what is mixed reality collaboration? It's quite similar to Zoom in many ways in that you have multiple people in different locations and they are all meeting up digitally. So where it differs is that users might be sharing virtual items such as designs or collaborating on shared 3D models. Users might be sharing a 2D representation of their room, as you are seeing right now, and they might also be sharing a 3D representation of the space around them, which can be viewed by remote headset users, as you can see here. So as this tech becomes more commonplace, these devices will be used at home in private locations such as bedrooms, lounge rooms, or in shared office spaces. And thus a need arises for a set of privacy tools that give users the ability to control exactly what they want to bring with them into the shared space meeting. There are a few existing solutions, but they are heavy-handed and imprecise in nature, and they redact huge regions or produce obtrusive blurring. And none provide granular object-level controls, giving users the ability to hide individual private items while still sharing the majority of their space. And that is where this contribution lies. It enables privacy in mixed reality meetings by providing users with object-level redaction tools to hide private items while still sharing the majority of their space. So what does that actually look like? Well, you're actually looking at it right now. Let me disable the privacy settings for you. The concept of privacy has been explored within the field of mixed reality for several years. Originally, as the technology was being developed, it was mainly explored from a hypothetical perspective. So, for example, if we look at the top right image, that's from a paper in 1998, which kind of builds a framework of what interactions with these privacy systems could look like. And it puts forward this vampire mirror, which basically only reflects public items, so that users can very quickly check the mirror to see what items are private, which ones are public. And it's these sorts of systems that really laid the groundwork for how we could go about building these privacy systems. So as the technology has developed since then, we've been able to do some more user studies into how users would actually prefer to have these systems built, but grounded in more real experiences as the technology is actually available. With those studies, we've found that users definitely have varying levels of preference in terms of how private they want to keep their surroundings. But one consistent finding is that users would tend to prefer a point and remove sort of system for each object. So they're able to look at an object, point and click at it, and have it disappear from public eye. So in terms of actual fully fledged systems that are attempting to build this, very little, basically none have been built so far. There have been little components that have been built along the way. So if we look at the middle image here, we can, this was from a paper that is looking at dynamically resizing the bounding box of a private region based on user movement. So as the camera moves around, we want to make sure that the object remains hidden and the encapsulated area doesn't kind of lose tracking. Yeah, so it did well with that particular component, but again, it's not a fully fleshed system. There's also the magic rope is probably one of the closest designs. And what this does is it gives users the ability to cordon off parts of their room with this rope. And so anything behind it can either be blacklisted or whitelisted. And the one mentionable thing with both the magic rope and the adaptive blurring is that they use blurring. And it's known that recently it's been discovered that traditional blurring methods is not they're not actually perfect at or perfectly secure. It's possible to kind of rework these blurring processes so that you can actually view the original content. So if you're trying to hide something that's incredibly private and cannot be viewed by the public, blurring is definitely not the way to go. So as we can kind of see from the existing solutions, they've been mainly hypothetical for a long time, and as we've moved into an era where the devices are actually becoming more commonplace, these systems need to be developed, and the components are there, but no one's been able to build a object-wise removal system. They've been quite heavy-handed, such as with the magic rope system outlined. Instead of using blurring to hide private objects, which has been found to be insecure, we're going to be leveraging a technology called diminished reality, which is quite similar to augmented reality in some ways, in that it modifies the world around you. However, instead of adding in virtual objects, we're going to be removing real-world objects through a process called in-painting. So in-painting has a couple of different approaches, one of which is an observation-based method, where the system views the content behind the object that's to be removed, and then transplants the background content onto the front, essentially removing it. Another approach that we'll be using is an AI-based approach, where we use neural networks to hallucinate and conjure up a potential background scene, and then paste that onto the front of the image, effectively removing the object. Diminished reality requires a few different components working in tandem to be realized. So for object detection, we've selected the YOLO model, which is quite fast and can detect up to 80 different items. For the in-painting model, we've selected the DSTT model, or Decoupled Spatial Temporal Transformer, and that also has a memory component added, and that we've found provides a good balance between speed and in-painting accuracy. Alright, so let's have a look at the system outline. So the scene is captured with the Z depth camera, and that streams a rendered point cloud of the space to the processing server. So the processing server is a centralized unit which does a lot of the different communications with the other components. At the core of it, it does object detection and segmentation. So it takes in the live feed from the Z camera, and it breaks down the scene into the various objects at play. It then sends data to both the in-painting manager and the headset. So the in-painting manager is its own separate component, and that is in control of taking an image and a redacted region and in-painting or filling that hidden region with potential background information. And that essentially simulates the object's removal. The headset application essentially hosts the user interface, and it is in control of the interactions that the user has with the system. So let's take a look at the flow of the system from start to finish of each frame. So initially the Z camera captures frames of the environment. That data is then passed to the processing server, which runs the object detection using a model called YOLO. So it breaks down the scene into the different objects, and then it ingests those objects and essentially maps those into the 3D space. So we have this set of 3D boxes encapsulating each item in the scene. That is then sent to the headset, so the viewer can then look around the scene and see all of these boxes around them. So should they choose to make an item private, they can point at one of those boxes and click, and that action will be sent back to the processing server, which then flags it as a private item. From that point, it'll remove any private items from the frame by cutting them out of the frame, and pass that to the in-painting manager, which then generates the in-painted region. That is finally sent back to the processing server, which then sends both the 2D image and the 3D point cloud, if required, to a remote viewer, and that is a privatized version. Let's take a look at the pipeline in action. So we've got a remote 2D perspective, the remote 3D perspective, which shows the point cloud, and also the headset perspective. So the user is able to look around and view all of the objects that have been detected by the system. They can then point and click at any object to privatize it, which essentially removes it from the remote perspectives. We can also see that the system dynamically adds and removes bounding boxes for selection as objects are introduced or removed from the scene. Real-time application is incredibly important to mixed reality systems, and that's because for headset viewers it is incredibly obvious if you're watching something that is not real-time through the headset, and it actually makes you feel quite ill as well. So it's been a very important goal throughout the project to ensure that the system runs in real time. So we've taken a few performance optimizations to ensure that this is the case. The first easiest one is upscaling and downscaling. So the original 720p input resolution image from the Z camera is dropped down to 360p, and that is then passed to the object detection model and also the in-painting model. So with that lower resolution, those models can run a lot faster because they just have less data to work through, and also don't have to produce as much data. As a result, there is a minor drop in quality, especially from the in-painting model. You get these slight pixelations in the in-painted region, but as long as the region is relatively small and not more than 30% of the screen, it's visually not noticeable, and yet you take away a massive performance benefit. The actual in-painting model itself has been a real challenge to get to work in real time. It's been quite a unattainable goal for several years, is getting one of these models to work in high quality and in real time. So the one that was selected is this DSTT memory modified model. It's quite lightweight and it's designed for speed. However, it didn't make the use of TensorRT optimizations, which is an NVIDIA model sort of foundation or framework. So in order to move it to that model type, we had to take the original PyTorch implementation, which is quite dynamic and Pythonic, and make it far more static with a load of internal modifications so that we could kind of export it to this new format. And that included a whole load of changes, such as a fixed input resolution. We had to modify the attention mechanism. The transformer blocks that do the in-painting hallucinations, they had to be made more static in how they are interleaved within the network. And one of the important things we did once we had exported it was use half precision. So these TensorRT models can run at FP32, which is 32-bit, or they can run at 16-bit. And that's just the length of the data kind of passed within the internals of the model. So using FP16 means we essentially halve the footprint, the memory footprint of the model, and greatly speed up inference speeds with a very minor hit to the accuracy. And finally, one thing that was actually quite a slight benefit to completely rebuilding the model is that we had to train it from scratch. So with that, we actually got to select some data sets that better matched the intended application of the system that were mainly indoors. And because of that, the model got very good at in-painting specifically within indoor environments where the system is most likely to be used. There are a few limitations to the system, so one of which is the in-painting quality itself. Because it's a real-time oriented application, it could not make use of the more modern and complex in-painting algorithms and models. And because of that, if there is a larger region needing to be in-painted, such as the fridge in this slide, you can see how towards the center you start getting interesting artifacts and gray areas, as it doesn't really know what the surrounding pixels look like, and kind of results in a bit of noise towards the center. There's also some issues with the object selection because it's dependent on the YOLO object detection model, which is somewhat non-deterministic. The objects can often kind of move in and out or fluctuate, which means that the hidden objects can actually pop back in occasionally. This, however, could be mitigated with the use of a more robust object selection system that utilizes both spatial anchors and the YOLO detection model, and that would result in a more consistent object selection system. Also for the depth in-painting, so the current model only in-paints essentially a 2D image, and as a result, once it kind of plasters those RGB values back onto the depth map, it results in these object ghosts appearing. So as you can see in this bottom image here, as I've been removed from the frame, despite the pixels being pasted onto the center of me, the actual depth mapping has not changed, and thus you can see this kind of ghost existing. So a variety of models have begun to be produced which attempt to resolve this issue by modifying the depth mapping as well as the RGB values. However, many of these haven't achieved true real-time as of yet, so future work could involve taking some of these depth in-painting models and applying them to this particular system and optimizing them for real-time application. To conclude, we have presented a novel privacy system which is capable of real-time per-object redaction for shared space mixed reality meetings. This thesis serves as a launchpad for exciting future work, bringing the development of comprehensive privacy tools from the hypothetical into the foreground of research.